introduce Ross Whitmore. So I met Ross when I was, well, what we call at UNK, visiting a professor at Winona State University. Ross was also a visitor for 2 of the 4 years, and he decided to do it Grover Cleveland style, so they were not consecutive. It was my 2nd and 4th year. The first time, I believe he was a sabbatical replacement, and the second time, I think it was for a maternity leave, plus they had a department chair that left, and so they were short someone while they were searching for another one. The second year, they actually gave him the old chair's office, so he actually had a real office. The first year, one of my students called it the cloffice, so it was really a tiny room where he could kind of lean back in his chair and almost touch the back wall. It was absolutely tiny. So we had a good time. I had a real office, he had this cloffice, and I think for about a month, I slightly irradiated him a little bit. Our lab guy, we ordered new Geiger counters, and the lab guy, rather than bringing them to the storeroom, he brought them to my office and just left them there. And I knew the Geiger counters were in there, and I guess I probably knew there were sample sources in there, but I kind of forgot about it. Those sample sources would have gamma ray sources, which of course would leave the box, and so, but anyway, Ross's wife is expecting, so at least he's managed to reproduce, so that was okay. I knew I didn't have to worry about such things, but there was hope for Ross. In any event, we had a good time, and then after I left Winona State to go to UNK, at the same time, he decided the Northern Hemisphere, he's had enough of it, and so it was time to go south. And south he went to New Zealand, but then even further to do some research on in Antarctica, which included field work, which is the stories of just doing field work in Antarctica was just fascinating. And he since has completed his PhD in New Zealand, and then is now a postdoc of some type at Monash University in Melbourne, Australia. And so with that, Ross, just take it away.
Good deal. Thanks, Jeremy. So just, Evan, can you help me, or can you give me the ability to share screen? Good deal.
Should be good
All
now.
right. So hopefully everybody sees a nice, pretty picture of a mountain right now. Give me a thumbs up if you see that. All right. So just moving into the talk, I'll talk through a few different topics. I'm going to start with a little bit of a history of the science of kind of Antarctica, and then also kind of how cosmic ray knowledge has progressed from, or over the last few centuries. And then I'll get into some of the research that I've done, specifically focused on kind of one of the 3 prongs of my PhD, which was actually looking at the evolution of outlet glaciers in the Victoria Land region of Antarctica. And I'll get into more specifics and details and stuff here in just a second. But just a little bit more about me. I'm actually born and raised from Colorado. So I did my bachelor's at the University of Northern Colorado, finished that in 2007. My master's from the University of Nevada, Reno in 2011, actually looking at structural geology. So that's the way that rocks bend and break, which is nothing even remotely related to what I did for my PhD, that I finished last year from Victoria University in Washington. So had kind of a left turn from the master's to the PhD, but all right, whatever. It's okay. It's really fun science. And that was what I was really after. It was something that was really interesting and engaging. So just a little bit of the kind of background, a little bit of the history around Antarctica. That'll be in kind of white, and then cosmic ray science, which will be in kind of a light blue. Now to start off, I would be remiss if I didn't actually acknowledge that, you know, Polynesian history extends way farther back than what European history does. And likely the first person to actually see Antarctica was a person named Uite Rongaura, and he actually took a small canoe. It's a small unadorned canoe called a Wakatiwai, from the island of Rarotonga in the South Pacific, and sailed 4,000 miles south, and actually was probably the first person to see the Ross Ice Shelf and Antarctica in general. Okay, and that was in about 650 AD that happened. Okay, so there are abundant legends throughout Polynesia and New Zealand about this voyage. Okay, which is a remarkable feat, you know. Then fast forward about 1,000 years, and you end up with what we kind of commonly call the Age of Discovery in Antarctic science. So this is between 1770 and 1880, or thereabouts. And really, it starts with James Cook's expedition in 1773, and these are actually the first Europeans to cross the Antarctic Circle. Okay, this really does kick off Antarctic science in general. Now, a few years after that, we have an interesting kind of major finding from Charles Augustin de Coulomb in 1785. So Coulomb invents this instrument called a torsion balance, and it's used to measure the magnitudes of electrical forces between charged objects. And what he notices early on is that the charge that this spontaneously discharges at some point, right? So he makes that observation in 1785. Okay, we build on that through the next several hundred years as to what's actually driving this. The next person to kind of mention is Fabian Gottlieb von Bellingshausen in 1820. His expedition was actually a Russian expedition, and these are the first people to actually circumnavigate Antarctica. And there are thoughts that they might have actually landed in a couple of places, but there are no real records of it. But if you look at the map tracks, which you can kind of see here, this is the map that they produced. You can see where the voyage actually sailed around Antarctica. And there are places where they get really close to the continent. Okay. The next one, in 1821, this is where we have John Davis, and he's the captain of a sealing ship. And he's a European, or he's an English-born American sailor who is probably the first person to actually set foot on Antarctica, on a Antarctic ice shelf. Okay. Then in 1839 and through 1843, we have James Clark Ross, and this is really the first expedition that does a lot of mapping. They actually map most of the coastline of Antarctica. And then finally, in 1844, we have Charles Wilkes, who claims to be the first person to have discovered Antarctica. So we have a long history of people kind of there. And then we have finally somebody that's like, hey, I found something, cool. Now, if we hop, or I guess it's not really a hop, but if we look at the next kind of age that we have kind of in Antarctic science, this runs from about 1880 to about 1920. It's called the heroic age. And a lot of you probably have heard of some of these people. The first person to really mention is actually Karsten Borchgrevink in 1899. This is the first time that we have a shore base established on Antarctica proper. Okay, it's called Camp Ridley, and the base is actually located in a place called Cape Adare. It's an extreme northern portion of northern Victoria Land. I can point it out here in a little bit if you'd like. The next kind of important discovery in the Cosmo world is actually by Julius Elster and Hans Geitel in 1899. And these two gentlemen actually experimentally show that spontaneous discharge that Coulomb had noticed is actually due to a highly penetrating ionizing agent. Okay, they're famous metal box experiments. Okay. Then fast forward a couple of years, and we get to Roald Amundsen in 1911. This is actually the first expedition to make it to the South Pole. That's quickly followed by Robert Falcon Scott's expedition. These are the second people to make it to the South Pole. Unfortunately, Scott's expedition actually perished within a few miles of a large depot that would have saved their lives. And if you're interested in reading some of the histories of these people, it's really this expedition in particular is really fascinating. You can read their journals, which is utterly tragic. Then the next year, we actually have another story that's reasonably famous, especially in Australia. Douglas Mawson's 1912 expedition. Douglas Mawson himself was an Australian Antarctic explorer. And this particular expedition is, I think, one of the most gut-wrenching that I know of. Mawson and two compatriots start exploring in kind of the area immediately south of Australia. Two of them die, and then he actually walks. He makes his own crampons and walks back to where they started from, a journey of many months. He ends up getting frostbite bad enough on his feet that he actually walks through the sole of his feet. It's an utterly astonishing tale, just in time to actually get back to watch the boat that he sailed there on sail away from him. So it's a pretty astonishing tale, and he ends up being a reasonably famous Antarctic explorer. Then in 1912, we also have Victor Hess's famous balloon experiments, where he actually discovers cosmic rays. So this is really the first time that we have evidence, or he produces evidence of this kind of particle shower that comes from above, not from below. Okay, and that's quickly followed a couple of years later by Werner Koester in 1914 with a series of higher balloon experiments that really confirm Victor Hess's results. And a fun fact about the last experiments that he was able to do, the last balloon flight that he had was actually the day that Franz Ferdinand was killed and basically started the First World War. So kind of a fun intersection of history there, or an interesting one, not fun. And then in 1914, that's when Ernest Shackleton actually leaves the UK for Antarctica for one of the most harrowing journeys that there's a record of thus far. This is the expedition where they take HMS Endurance to Antarctica, and it's actually crushed and lost in a bunch of pack ice. But Ernest Shackleton, being the leader that he is, actually safely gets all of his sailors safely back to port over the span of many, many years. A truly astonishing journey across the Southern Ocean. And he gets them back just in time for the men that he saved from Antarctica to go die in the fields of Flanders in France during the First World War. There's amazing history to kind of be had in the heroic age. It's really, really fascinating stuff. Now, if we hop to the next kind of time frame, it's the technological age. This is from the 1920s to the 1950s. And this is really when we start seeing explorers start to bring newfangled contraptions to the continent and start to try and explore a little bit farther beyond what, just a pair of human legs or a dog's leg can really do. Okay, so to start off, we have just a Cosmo comment. Robert Milken in 1928 actually sets out to disprove cosmic rays. He sets out to disprove Hess and Koester, and ends up proving that they exist, and ends up naming them cosmic rays with a series of experiments looking at charged particles submerged underneath lakes at different elevations in the US. Okay. Then we get in Antarctica, we get to Douglas Mawson's 1931 expedition. And this is really the first time that what we'd identify as like really fundamentally new technology has been taken to the continent. Okay, so they have cameras that are capable of recording moving images. They take an airplane. So really what you're looking at here are the first moving images from a plane in Antarctica. Okay, so this is kind of a momentous occasion, and it's pretty fascinating to watch, actually. Now, moving on from there, in 1934, A.B. Gross is the first to hypothesize that cosmic rays can produce radiogenic nuclides in the Earth's surface. So this is really, really kind of foundational stuff for the science that I've been doing. Okay. Then 4 years later, Pierre Auger in 1938 discovers the secondary cascade of particles. So now we know that it doesn't just go, it's not just one particle traveling from interstellar space and then hitting the ground surface. It's actually a whole cascade of secondary exotic interesting particles. Okay. Now, if we hop back to Antarctica, briefly, we have Richard Byrd and a series of expeditions from the 1930s to the 1950s, where they do a huge amount of mapping and reconnaissance of the continent itself. And Richard Byrd's 1947 to 1948 expedition is actually the first expedition to fly over the South Pole. Okay, so that's a big accomplishment. You know, we're still in the era of firsts in Antarctica. His right-hand person, as it were, Finn Ronay, from 1946 to 1948, is actually in charge of mapping thousands of square miles of Antarctica. So he's really the person in charge of a lot of the maps that we have, and a lot of the names that we have around Antarctica right now. And then finally, we kind of roll it up with the technological age with Vivian Fuchs and Edmund Hillary's expedition in 1957, where they established the New Zealand base called Scott Base, and then actually took tractors from Scott Base to the South Pole and back. And you can actually see, if you go to Christchurch, there's a museum that has a series, or that has one of these tractors still preserved. And a few years ago, about 3 years ago, they actually drove one of the tractors from the south tip of the South Island to the north tip of the North Island, just to show that it still worked. And it does, it works just fine. Then we kind of move into the scientific age, right? So this is from about 1950 to the present, okay? We have a series of different kind of rapid advancements in both cosmoscience and then also in Antarctic science, okay? So the first one for cosmoscience is actually Raymond Davis and Oliver Schaefer in 1955 proposed that cosmogenic nuclides could be produced in the Earth's surface, and that could be applied to geologic problems, okay? So this is really the first time that somebody's like, oh, well, we could probably use these things to answer some geologic questions that we have, and there are a series, a whole host of different questions to ask. In 1967, Devendra Lal and Bernard Peters actually provide the theoretical foundation for exposure dating. Okay, so the science that I've been doing actually dates back quite a while. I mean, the real foundation is laid here with their work. In the Antarctic front, we have Johannes Wertmann in 1974, who proposes a hypothetical mechanism that could produce rapid grounding line retreat of large ice sheets. Okay, we call that the marine ice sheet instability. And it's this idea where you have a perturbation caused by warm water at the very base of the glacier that actually changes the position of what we call the grounding line. It's the zone between where you have kind of thick ice that's grounded on the sea or on the sea floor, okay, and the transition to where it's actually floating. So you have this little floating lip called an ice shelf. So it's the transition from an ice sheet to an ice shelf. That's the grounding line. So when you actually start to thermally erode that, you can get this runaway retreating grounding line, and then also thinning ice surface from this mechanism. And you can actually set up a series of positive feedbacks where the glacier is actually retreating because the glacier is retreating. Okay, so this is potentially a very catastrophic mechanism. And just to kind of hop forward a little bit, we think that this mechanism is actually operating in Western Antarctica right now at Pine Island and Thwaites Glacier. Okay, so this is the mechanism that we think is running there right now. Now, if we hop to a little bit farther in the future, we have Richard Muller in 1977, who's the first person to really demonstrate that accelerators could be used to identify light radiogenic elements. Okay, so here's a 7 MeV AMS that I was able to visit in South Korea. Yeah, so that's the instrument that we actually count the number of atoms that we have in the rocks on, okay? And then finally, to kind of take us up to the 2000s, we have Christian Schuf's work, who actually shows mathematically that Wertmann's ideas are sound and that we may be able to actually predict them. Okay, so this is a watershed, effectively, of being able to model these systems with computers and really start to understand how integrated different parts of the system actually are. Okay, now that's enough of the history side of stuff, but it does bring us nicely up to kind of current observations of Antarctica and changes in the ice sheet there. Okay, so what we've been able to do over the last about 50 or 60 years or so is use satellite observations to really understand kind of changes in the ice sheet or in the ice sheets themselves. Okay. Now that's great, and the image that I'm showing here is actually one of the most recent studies. It's actually looking at ice surface elevation across all of Antarctica. Okay, so where you have these hot colors up to kind of a purple and black, like you see here in West Antarctica in the Amundsen Sea sector, that's where you have extreme amounts of ice surface drawdown. So the ice surface is physically going down there. Okay, and you'll notice that there are a few other areas. There's a nice hot spot right around Totten Glacier, right around Denman Glacier and the Amory Ice Shelf, and then a few spots along ice shelves along the Queen Maud Coast. Okay. Now you'll also notice that there are a few areas where we have a slight positive anomaly. So the ice surface is physically going up there. There's either more accumulation or something mechanically is happening to let that ice surface go up. But fundamentally, you know, what I hope you take away from this is that the ice surface drawdown in Western Antarctica, specifically around Pine Island and Thwaites glaciers right here, is dramatic. It's significant. And again, this is where we think we have the marine ice sheet instability mechanism operating on the system. Okay. Now, these observations are great, but they only extend back a couple of decades, right? They only extend back as far as we have satellites in the sky for. Okay. And really, a lot of these aren't long enough to really know if the change that we're seeing are noise in the system or actual real change. Okay. Now, ice sheets do change on decadal scales. That's just a fact. But we don't really understand how they function on centennial to millennial time frames. Okay, so we don't really have, you know, using satellite imagery and satellite data, we don't have an understanding of how these things change on the hundreds to thousands of year time scale. Okay, which is really important if we want to understand kind of past climate and then where we're going with our future climate. Okay, so there's a technique that we use using cosmogenic nuclides in the rock surface. That lets us expand that history, you know. So I'm just going to highlight one little area right here. We'll go into more detail on how these plots are made. But there was a study done in 2017, and this is just one of many. But this particular study extends 3 very large outlet glaciers, the ice surface history of those 3 very large outlet glaciers, up to 20,000 years. Okay, so we're looking at, instead of a few decades, you know, 50 years, 60 years, 20,000 years worth of ice surface history. Okay, so this really gives us so much better perspective on how these outlet glaciers function on exceedingly large timescales. Okay, now I'll explain a little bit more about kind of how we do this, and fundamentally what we're using are particles produced by cosmic rays. Okay, so I'm just going to show you a cloud chamber real quick. What you'll see are alpha and beta particles, and then maybe some muons and maybe some protons. You can think of a cloud chamber a bit like contrails that you see when a jet's flying at high altitude. You'll have kind of the particle come through, and then a kind of cloud of material that forms behind it as the ionizing particle kind of charges the particles around it, the particles of alcohol around it. Where you have really straight tracks, it's high energy. Where you have kind of curved tracks, it's lower energy. Where you have you'll see a few very thick tracks, those are actually alpha particles, and the thinner stuff are the kind of smaller particles. So just to let that play for a second, so you can see the radiation, the natural radiation that we have from cosmic rays around us all the time. There's no source in here, there's nothing like that. This is just atmosphere. This is just what we have in the atmosphere. And you can see all of these wonderful particles that are just spinning around and shooting through the cloud chamber itself. Now, this is the stuff that we're actually using, or that we depend on to do the science that I've been doing. Okay. Now, what we're using are actually the nuclides, the either radiogenic or stable nuclides that are produced in the ground surface from those particles. So we have a series of different nuclides that we can use. So we have helium-3 and neon-21 that are stable nuclides. We have beryllium-10, in situ carbon-14, 26 aluminum-36 chlorine that are radiogenic that we can also use. They have different half-lives, so different nuclides actually give you different information. And fundamentally, what's happening here is we have a primary cosmic ray that comes slamming into the Earth's upper atmosphere, produces this secondary cascade of particles. That secondary cascade of particles produces in the atmosphere a host of different nuclides. But what we're interested in is when that cascade actually hits the ground, when it hits the ground surface and hits a particular mineral and a particular atom. Okay, so the work that I've been mostly working with is actually beryllium-10. And so that actually requires quartz because we're using that oxygen-16 as the parent or the parent atom. Okay. Now, critically, nuclides are produced in the rocks by cosmic rays. The production of those nuclides actually is predictable, and the rates actually vary with altitude and with latitude. So as you go higher up a mountain, you'll actually accumulate more, and as you go closer to the poles, you'll actually accumulate more. Okay. Now, one of the cool things is that the nuclides really only start accumulating when that sediment or bedrock is exposed to open sky. Okay, so if we have an ice sheet or a glacier that's kind of covering that land surface, it's insulated. That ground surface is actually insulated from the cosmic ray flux. Okay, so that's actually really helpful for the work that we do. Okay, and finally, we can use these to explore geologic questions. So I'm going to be talking a lot about kind of how it's impacted glaciology and glacial geology, but similar impacts have been had in recurrence intervals on faults on relatively short time frames, on volcanoes, all kinds of different stuff. So the kind of methodology that we use is colloquially called the glacial dipstick. Okay, and you'll see a bunch of these plots as we move through the presentation. Effectively, what you have is an age elevation plot. So we have age along the x-axis right here, and elevation along the y-axis right here. Okay, and the thinking is that we have some glacier. This would be a cross-sectional view of a glacier. It's either flowing into the screen away from you or flowing out of the screen towards you, whichever way you want to visualize it. And it's sitting on a nunatak, a bit of rock that extends above the ice surface. And in that ice, we actually have sediment that's transported inside the ice. Ideally, I've kind of exaggerated it here. Ideally, we want sediment that's actually traveling right at the base of the glacier, right at the base of the ice. And I'll talk about that more here in just a second. But to make one of these plots, if the ice surface actually drops, if it thins a little bit, it'll drop one of those cobbles out. And when that cobble is dropped out, that's when the cosmoclock starts. Okay, so if we have in time 3, the ice surface drop a little bit more, drop another clast off, you can see that now we've plotted 2 points on our age elevation plot, right? So if we go to time 4, we'll plot another one, go to time 5, the ice is gone, and now we just have a few glacial erratics that are strewn along the mountainside that preserve the ice surface elevation history. So we go from the oldest to the youngest. Okay. Hopefully that makes sense to everybody. Now, we don't just go out and pick up any old rock. We go to very specific places, and we have very specific criteria to help us look for stuff that's in what we call the zone of traction, stuff that likely has not seen a prior exposure history, which ends up complicating our results. We'll talk more about those in a little bit. But we go to sites like this. This is from the David Glacier. Just to give you some sense of scale, the David right here, I believe, is about 10 miles across. Okay, so it's a fantastically large glacier. We go to areas where we have this kind of sculpted bedrocks. We have all these nice kind of rounded curves on this bedrock surface. We're actually walking on a granite right here. And on that surface, on that kind of smooth, glaciated surface, hopefully you notice that there are some stripes in the bedrock surface itself that run along, they're in the same orientation as the glacier. Those are called glacial lineations or glacial striae. Okay, so that's where the glacier is actually hauling sediment at its base and it's scraping along the bedrock surface to excavate these little grooves. Okay. The other thing I hope you notice is up here where it's kind of shiny. That's where we actually have a little bit of glacial polish. So we have really fine, kind of very, very fine grit in the ice as well. And that's actually going to abrade the surface and polish it. Okay. Now, what we're interested in are all the rocks that are kind of peppered on the surface here. Okay. So what we're interested in are collecting these glacial erratics in a transect. Okay. Now, those glacial erratics have to meet certain criteria. For me, I was looking for quartz. So that's obviously a big factor. I have to have rocks that have quartz in them. So this is a granite. We look for rocks that are precariously perched. They're striated, faceted, and bullet shaped. Okay, so this particular cobble, it's about that big, just to give you some sense, because I know there's no scale here. it's sitting right next to a little drop. So if it was going to move, it would have. If it was going to move, it would have fallen off. And then you can see one little tiny pebble right there. And when we picked this up, it was actually sitting on 3 tiny, tiny little pebbles. So we're working like little ball bearings, which is actually really what we want to see. We want stuff that's reasonably metastable, okay? Just so we know that if anything had happened, if it was going to move, it would have moved, okay? Now we also look for glacial striae, very fine glacial striae on our rocks, and then also faceted surfaces and some amount of shaping that kind of makes them more dynamically able to move through the glacier. Now, all of this, why I'm saying all of this is because these are the characteristics that we look for erratics that are plucked from the glacier's bed and transported along the base of the glacier and never see open sky. Okay, so they don't have a prior exposure history. Okay, that's why we really focus on these type of samples, because once you start getting multiple exposures, you're still going to be accumulating those nuclides and you're going to really muck up your data. And you'll see, trust me, you'll see one of those here in a little bit. One of my data sets is really gnarly. But if we just move on and kind of start talking about Antarctica in general. So I was focused on the Ross Sea region. Now, just to give everybody a little bit of perspective here, we have the East Antarctic ice sheet kind of on the left. We have the West Antarctic ice sheet on the right, and they're divided by the Transantarctic Mountains right here. Okay, so those are the Transantarctic Mountains. Oh, let's see. Now, the area right here in the center of the frame, the kind of white area is the Ross Ice Shelf. The bluish area up here is the Ross Sea. Okay. Now, I was working in the Victoria Land region, which is right here. And for anybody who knows Antarctic or I guess the Ross Sea region, this is Ross Island, and then this is Coolman Island. Coolman Island will become more important here a little bit later. Now, what's cool is that these ice sheets actually drain through huge glaciers. So in West Antarctica, we have these large ice strings that aren't actually confined by topography. The ice is actually thick enough that it will move over the topography without being really inhibited by it. Okay. For East Antarctica, an ice that's moving from kind of the ice sheet there out into either the Ross Sea or the Ross Ice Shelf, it actually has to traverse the Transantarctic Mountains. And we call these, because they run through these kind of confined fjord valleys, we call these outlet glaciers. Okay, so that's really what we're looking at here, are a series of different outlet glaciers along a huge portion of Antarctica. Now, we can use these to do some really interesting science, to actually work out what the thinning histories are of, or what the glacial history of, these parts of Antarctica are. Okay. Now, I focused specifically on Tucker Glacier, kind of in the north up here, and then Mawson Glacier down here for this part of my PhD. So I'll start in with the work that we did at Mawson Glacier. Mawson is an interesting one. So this is from, we had a sampling campaign there in January of 2016. We went to 3 different sites, Bruce Point, Mount Murray, and then Mount Gauss. And north is actually down, just so everybody's kind of oriented there. So you have Bruce Point, Mount Murray, and Mount Gauss. And I know it's kind of difficult to keep, maps in your head and all that stuff. So what I've done is actually take a panorama picture and I've annotated it. So we have the Nordenskjold ice tongue that we're flying over right now in the helicopter. If you look out at the horizon out here, that's actually the East Antarctic ice sheet. Okay, so that's actually the giant ice sheet that's out here. Okay, we have Bruce Point kind of down here in the lower right. We have Mount Murray just above that, and then across the glacier, that's about 7 miles across, we have Mount Gauss. So the data sets that I'll talk about from here are Mount Murray. That's the one that I was able to work on, and then Bruce Point, one that one of my colleagues was able to work on. So to start with Mount Murray, now what you're looking at again is just an exposure elevation plot, an age elevation plot, and you'll see that there are kind of 2 populations here. We have one population of data that is sitting right there, that's actually our thinning history, and then we have a second population out here that's rocks that have a prior exposure history. And we can talk about more of the dynamics of the glacier and why those rocks are the way that they are later if people want. Now, just to kind of clean this little zone up and look at the thinning history itself, what we see is a relatively rapid thinning. Okay, so this is actually cracking the ice surface through elevation over a few hundred years. Okay, so at Mount Murray, we have about 160 meters of ice of ice surface drawdown over a few thousand years, and the really dramatic portion is right around 5,000 years ago. And what's interesting is that this event, this thinning happens really fast. Okay, we're talking a couple of hundred years, and that glacier is really thin. Okay, now what we do is take the core of that thinning, the core of that really intense thinning signal, and we do some advanced statistics on it. So this is a 10,000 iteration Monte Carlo simulation looking at or trying to calculate the thinning rate of the core of thinning, the core of that really intense thinning. And what we find is that we have rates in the geologic record that are similar to rates that we have in West Antarctica at Pine Island and Thwaites Glacier today. Okay, and we know from our data that these events last for potentially a few hundred years, and Pine Island has really only been going for a few decades at most. Okay, so that's something to keep in mind. Now, if we hop to Bruce Point, about 10 kilometers to the west, Bruce Point has a very similar thinning history because it's part of the same glacier. So we have a nice core of thinning. You can see that there are only a couple of outliers here. We'll talk about that. So we have the nice core of thinning right here. Kind of clean that up, remove all the extraneous bits, run some statistics on that, and we get, again, a very substantial amount of ice drawdown that is still analogous to what we see in West Antarctica today. Okay. Now, what's interesting, since we have these kind of terrestrial records, what does this actually mean in context of the region that they're in? We can actually use some other data, some other geologic data to really start to investigate these questions. Okay, so what I have plotted here is another map. We have Mawson Glacier right here. That's Mawson. The black lines that you see in there are indicative of where the glacier is actually flowing. They're glacial. We call them glacial lineations. It's just basically where the ice is actually physically moving. And the kind of colored thing underneath of that is actually ice velocity, with red being the highest and then kind of blue being the slowest. Okay, so you can see that Mawson itself has this kind of zone of high intense, fast flowing ice. If we look just to the south, this is about 100 kilometers to the south. Mackay Glacier also has that same kind of fast flowing ice. We'll talk about Mackay more here in a second. Now with Mawson, just focusing on Mawson, understanding that the position that the grounding line is in, the position that every bit of that glacier is in right now isn't what it was, say, 10,000 years ago or 20,000 years ago. Okay, now to track out where this glacier had advanced to, at some point in the past, we can use geomorphology, so the land surface, to actually really inform us or inform our understanding of how these systems function. So what I have drawn here, the white lines are what we call megascale glacial lineations. These are features that are formed at the bottom of a glacier, that are formed right at the soul of the glacier, that actually track where that ice is moving as it's expanding. Okay, so this is really showing us how this glacier moved and where it went 10,000 years ago, 20,000 years ago, right? So this is actually showing us where that ice went. Now, the other feature that I have mapped on here, these kind of fuchsia lines, are another landform called a grounding zone wedge. Okay, grounding zone wedges form when the ice sheet is actually retreating, when the grounding line is actually moving backwards. So where that grounding line is actually relatively stable for some period of time, it'll deposit this little wedge of sediment. Okay, so that's what you're actually looking at with the fuchsia lines, is really how the ice sheet, how the grounding line changed position over time. Okay, so we have in white kind of showing us where it's advancing to, and then in fuchsia how it's retreating. Okay, we have both the birth and the death of the system shown in kind of the geomorphology here. Now, some of the other features that you hopefully notice here are a series of sediment cores that have been dated throughout this portion of the Ross Sea. And there's one right off the coast of Mawson, right here, that puts an age at the transition from totally glaciated. So using the stratigraphy there, we can actually work out the facies assemblage to show when it was glaciated, when it had an ice shelf, and then when it was open ocean, okay? And what we see with this sediment core is that it basically goes from glaciated to open ocean almost instantaneously. There's no ice shelf facies there. And that's been dated at about 5.9 thousand years ago. So all of that really helps us piece together what's going on land as well. Okay, so that's actually really cool. Now, if you pay attention, or if you're paying attention to this, you'll also notice that there are a series of lines that kind of come down and connect into the main trunk that's coming off of Mawson. And those track back to Mackay Glacier. So you could hypothesize, you could think, well, shouldn't those respond at least somewhat similar to one another? And the answer to that is yeah, they do. Well, I'll show that here in just a second. But this part of the system, even though those are 100 kilometers apart, respond very similar to one another. And if you go 100 kilometers to the north, down to the bottom of the page, there's another glacier that's actually exponentially larger than these two that drains about 250,000 square kilometers. It's about the size of Colorado, through one outlet channel. Okay, and that has an identical thinning history to these two. Okay, I'll show you that here in a little bit. Now, why our work is actually really useful is we have a series of kind of data of models that track ice surface elevation changes through time. And so what I've plotted here are 5 different models and 7 different model runs that show how these different models have kind of tracked the ice surface elevation for Mawson Glacier specifically over the last 15,000 years. So each one of the different colors is actually a different model run with a different model run. Okay, and hopefully what you notice is that there's no similarity in the rate, the timing, the style, or the magnitude of thinning, of any of these glaciers, or of any of these outputs, okay? So we have stuff that extends back to, just about 14,000 years ago. We have ice that's a few hundred meters taller, 500 meters taller, potentially a lot more, depending on if you're in the green or orange. And they thin differently. So these are kind of synthetic outputs. If we use what me and my colleagues have been doing and actually put real dates and rates and all that stuff and plot those on the same graph, what we notice is that our data, so the black data are the work from Mawson Glacier, and the gray data are from Mackay Glacier. They plot identically over each other. Okay, so we have a similar signal at both of those glaciers 100 kilometers apart. And that similar signal is completely different to anything else that the computer models have been producing. Okay, and there are probably a few different reasons for that we can go into kind of in the Q&A session. But fundamentally, our data are actually really useful for thinking about, ice surface histories and applying them using computer models. Okay, so I'll move on from there. We can talk about this more here in a little bit if people want. To the next glacier that I was working on, Tucker Glacier in extreme northern Victoria land. So Ross Island is where Scott bases. It's the Kiwi station. And this is about 600 kilometers north of that. It's very, very, very difficult to get to. And this particular outlet glacier actually isn't connected back to the East Antarctic ice sheet. It's just basically a really, 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 really big alpine glacier. The catchment on this thing is somewhere about 12,000 square kilometers worth of catchment. So we're talking huge, okay? And another kind of important point to make here is we don't really understand the maximum extent of grounded ice in the Ross Sea through the last glacial maximum. Okay, there are studies that put it at Coleman Island. There are studies that put it out to the continental shelf break that's about right there. We'll talk more about that here in a little bit. But really the reason to point that out is Tucker Glacier is actually ideally positioned to answer some of those questions just because of where it is. Okay, so if we start into kind of thinking about sample locations and all that stuff, there was a sampling team there in 2014 that collected rocks on the south side of the glacier, and they actually pointed us to the north side. We went there in November of 2016 to collect rocks on the north side of the glacier. And really what I'm going to talk about is kind of a combined data set because of the positions between these two locations, the shark fin and Hef's Manor, kind of how they relate to each other, because they're analogous. They're at analogous positions in the outlet glacier itself. Now, again, as I said before, it's kind of hard to keep visualizing where these places are. So this is actually from a place called Beans Bench. You're looking at Tucker Glacier right there. It's flowing from the right to the left. So on the left side of the screen, where you have that kind of horizon out there, that's actually ocean. When you go to the right, you're going into some of the most inaccessible mountains in Antarctica. Yeah, so there's Tucker. Hef's Manor is this little snowy mountain right in front. And then about eight miles away, that little tiny stripe of land is the shark fin. Okay, so again, these outlet glaciers are absolutely massive features. Now, what I've done is actually plot all of the data together as one large compilation. And this is from several different people's effort and people's work, and is actually using both beryllium and in situ carbon-14. So the blue points that we have right here, those are my data set, or that's my data set, with using 10 beryllium. The red data set here is actually from Greg Balco, also using 10 beryllium. And then the yellow data set right here is actually using in situ C14 on samples that have been run using beryllium by Brent Goering. Sorry, I forgot his name for a second. So really, the system is very complex because of the large mountains around it. So that's why we end up with this really scattered, complex exposure history stuff out here. But we are lucky enough to have enough samples. This is something like 50 samples to pick out a thinning history from this. Now, it's a little bit different than what we saw in southern Victoria Land, so I've just isolated that. What we see is that we have about 300 meters worth of ice surface drawdown over about a 15,000 year time frame. Okay. Now, that's much slower than what we see in southern Victoria Land with Moss and Mackay data. Okay? Now, we do the same thing. We run some statistics on this, and we find that, yes, indeed, it is much slower. Now, what's causing that, right? So if we go back offshore, we look at what's kind of going on offshore, we don't actually have a record of any grounding zone wedges or megascale glacial lineations, not because they didn't exist at some point, but because there's actually been a huge number of icebergs, large icebergs, that the keel has actually scoured the bed surface and totally plowed it up. So you actually completely obliterate almost all of the features that you see there. Now, what's not shown on this map is a grounding zone wedge right here by Coolman Island, and another grounding zone wedge. And remember, that's where we know that the ice or the grounding line is relatively stable for some period of time. And there's another grounding zone wedge out here that's a lot more beat up. Okay, so these are where people really kind of hypothesize, oh well, grounded ice, the maximum extent of grounded ice must have been around Coolman Island. Oh no, it must have been out near Marbre Bay. Okay, and again, Tucker is right there. This is an ideal place to investigate. So building on that, we can actually use computer models to inform some of what's going on here. Okay, so these are 4 different regional computer models that are showing 2 different behaviors. We have one kind of data, or one set right here, where you have this extreme over thickening of Tucker Glacier, and then this really rapid thinning event, or relatively larger over thickening, and then a relatively faster thinning history over a shorter period of time. And then we have another kind of end member where we have kind of this relatively minor amount of overthickening, and then this really long time frame of thinning, okay? Then it just kind of settles out. Now, if I plot our data on this, hopefully what you notice is that our actually constrained beryllium and in situ C14 ages really start to align with this kind of bottom group down here. Now, what's cool about the difference between these two populations of models, this population up here actually puts grounded ice all the way out to the continental shelf break, okay? So this ice much farther out. And that's what's producing this really rapid response, because you undergo what's called the marine ice sheet instability with an overthickened Tucker Glacier, versus this population down here that actually has the grounding line at Coolman Island and then an ice shelf right in front of these, right in front of Tucker Glacier. So that's how you get the two different responses. So we can actually answer some of those questions as to like how far extended grounded ice was in the Ross Sea during the last glacial maximum with this data set. Now to kind of build on this a little bit more and give you kind of a more regional picture. So we just talked about Tucker Glacier up there in the north. Now I've plotted, or one of my friends has actually plotted the data sets from David Glacier, Mawson Glacier, and Mackay Glacier in one plot, okay? What we see is, again, that really abrupt thinning signal that's hundreds of meters of ice surface drawdown over a few hundred years, right about 6,000 years ago, okay? That's a very distinct signal. And the reason why we have two data points out here and that are gray, that are from Mackay Glacier, and none from either Mawson or David, is because we actually physically run out of mountain to be able to sample for ice that's thicker than that, okay? So we just can't get to where the ice would have been in the past. So we don't actually have an upper limit on the thickness of either David or Mawson Glacier. Now, if we go a little bit farther to the south in the central Transantarctic Mountains right here, this is actually that same plot that I showed you right at the beginning from Spector et al. 2017. And what they're doing and what they show is actually, what they do is capture kind of the longer term signal, this kind of much less, I don't want to say this, it's a much different signal because of the position in the actual catchment of where these nunataks are. Okay, so this actually records the ice surface over 20,000 years or so and shows the behavior. Now, what's cool is we can actually tease some things apart here and work out why Mawson, Mackay, and David are actually functioning the way that they are. Okay, so let's kind of jump into that and talk a little bit about the hypotheses for deglaciation in the Ross Sea region over the last about 20,000 years or so. So there was an idea called the swinging gate model, or swinging gate mode, that was put forward in the early 2000s, and it's a really simplistic idea where you have grounding line shown with the dashed lines here, and the grounding line basically just moves very systematically from north at Coleman Island down south and farther south to the Cycle Coast where it is today. And it's just a very simple idea of, you have this swinging door of grounding line retreat. Okay, that's probably not accurate given everything that we've seen. The next kind of more complex model or mode is colloquially called this saloon doors model, or saloon doors mode. And it's actually where you have grounding line retreat initiated in the central Ross Sea out here somewhere. And then that grounding line retreat propagates both to the east, to the south, and to the west. So it kind of makes this ever expanding arc, okay? Now, the problem with both of these is that they don't really take into account the bed surface and the bed geometry. That plays a big role in kind of how the grounding line moves through these areas. So the next one that we have to talk about is actually using geomorphology, the bed surface, and trying to inform kind of what's going on with grounding line retreat over the last 20,000 years using that. Okay, and this is a much better representation. And hopefully what you notice, here's Ross Island, that's Mackay Glacier right there, that's Mawson Glacier, that's David Glacier right there. And all three of these are actually behind this nice big salient where you have this relatively stable extended grounding line. Okay, so you have this relatively stable area for some period of time. And then the most recent, actually, people have taken and done a whole bunch of work with sediment cores and dating them. And you actually see a much more or you see much more resolution on kind of how the grounding line has changed through time. So you can see that up here at Mawson Bank, you know, ice stuck there for a long time. On the Prairie Bank, ice stuck there for a long time. And once you get down into here, the sediment core ages that I talked about haven't been published yet. Those are one of my friends. But what has been published is actually kind of dubious. So you're actually looking at something that's probably about 5,000 years ago when that actually retreated. But again, we have this nice big salient of kind of grounded ice that's producing some of that stability to keep those, to keep Mawson Mackay and David Glacier kind of a little bit thicker. And then when that finally collapses is when you get that overall drawdown, which is, I think, kind of interesting. Now, the other thing that we can do, I've mentioned numerical modeling a little bit, we can model the whole system. Okay, so this is all of the Ross Sea region, shown in black right here. There's Northern Victoria Land. That's actually Cape Adare right there. If you rewind for a little bit, Ross Island would be right there. And what they've done is actually smooth out a lot of the topography in the Ross Sea region. So you actually miss like the Mawson Bank right here. You have a very subdued Prairie Bank right there. But it's all in the name of kind of efficiency for the model. So this particular study actually does 3 scenarios where they have kind of a warm scenario and they look at the grounding line retreat in that warm scenario. So what their initial conditions start with the grounding line out at the continental shelf break, and then they evaluate how the grounding line has changed position over the last 20,000 years. So with the warm scenario, you know, we have this nice big gap between 13 and 12,000 years ago that's, you know, removing all of that ice that I was just talking about. That, you know, there's a lot of complex topography right there that's actually keeping ice out that far. Then if we move to the kind of moderate scenario where they have slightly cooler ocean temperatures, you see that the grounding line retreat pattern is actually a little bit different. And then if you move to their cold scenario where they have relatively cold water interacting at the bottom of the ice sheet, you see that the retreat pattern is again very different. And I mean, a thing to highlight is that all of them get kind of the Western Ross Sea wrong, but that's because they oversimplify the topography. But you know, these are ways we can start to think about, okay, well, what has the Ross Sea region done over the last 20,000 years? How has this functioned? You know, how much has this contributed to global sea level rise? Or, you know, how can we use this to inform our understanding of future ice laws? Okay. And particularly for the Western Ross Sea, this bit right here, it's very analogous to what we see in Western Antarctica right now at Phenomenon Waits Glacier. Okay, so just to kind of wrap things up with why do we actually care about any of this? Well, we have a complex deglaciation from the last glacial maximum, and we can see that now with much more clarity using, you know, terrestrial cosmogenic nuclides and dating the sea floor and features on the sea floor. We can build a better picture than just letting models run on their own. Okay, models are great, but to some extent, you know. Another important thing, this provides real perspective on how the West Antarctic ice sheet and other areas that are grounded below sea level may respond to warmer oceans. Okay, there are a series of different big basins that could potentially produce, you know, 1 meter or more of sea level rise in East Antarctica. You know, it's not just West Antarctica we really need to worry about. And really, this helps constrain the maximum extent of grounded ice in the Ross Sea, which is, again, useful information, especially because that provides a better assessment of the overall Antarctic contribution to sea level rise over the last 20,000 years. So I'd just like to say thanks to a whole host of people. In Antarctica, you don't get anywhere on your own. It's all team effort, for sure. And so these are some of the people who have made that happen. And my partner, who actually did her master's in Antarctica, and she was the first person that was like, yeah, you can totally do science there. And I was like, what, really? Because I was kind of a moron. But anyway, I'm happy to take questions right now. But thank you for letting me talk at you.
All right, so I'll throw the first question out here then. So how long were these trips to Antarctica for you? And what's something that you were not prepared for that you got there and you were like, I wish I'd have known more about this before I'm stuck here?
Yeah, so that's a great question, actually. For me, I had 3 trips down that were about a month each. Okay, some a little bit more, some a little bit less, but about a month each. And it's funny, the old adage, so you don't know what you have until you don't have it anymore, or until you've lost it. But honestly, I gained such an appreciation for my family and my friends and the people around me there. It wasn't so much the physicality of the work, for which Cosmo, I mean, I've done a lot of geologic field work, and Cosmo is by far the most physically challenging work that I've done, because you're literally hauling rocks that big in a backpack full of them all day, along with steel chisels and rock hammers and sledgehammers and a rock saw and batteries for the rock saw, and then a gas-powered rock saw and gas-powered rock saw. You're carrying so much stuff that, like, physicality of it is intense. But that the thing that I guess really struck me, or that I learned there, was how important my partner is, how important my parents are, how important my family and friends are. It's there's something about the isolation that really gets you thinking. I mean, and the other thing that I learned, and this is going to sound really cliche, but it's true, is I actually learned that there was some stuff that I was holding on to in my life that just didn't matter. It just didn't matter, and I just let it go. It was just a wave of forgiveness. Honestly, it was my second trip down there. It's like, I don't give a crap about this stuff anymore. And I wrote to the people who had done the thing, and it was just like, I don't care. We're good. Do what you got to do. And so it's weird for me. It was more those intangibles that were just thrust in my face, because I mean, you're living with the same 3 to 4 people for a month on the ice. You know when they go to the bathroom, when they wake up, what their eating habits are, everything about them, because you're living so intimately with them that, for me, the only place that I had to go, and I don't mean this in a bad way, but there was solace and refuge in myself, and really kind of taking the time to evaluate who I am and what I want to do and what I stand for. And it was transformational for me, to be really honest. And honestly, the first trip, I learned, because I had been to places that not many people get to go, and so when you physically leave a footprint there, you feel kind of bad. And it was the physically leaving a footprint there, and then it's like, oh, well, that's probably not going to go away for the next 200 years, and then like having that kind of aha moment of, oh, but carbon footprint, right? Like it was, I don't know, there are just wires that crossed, and was like, oh God. Like I came back a very different person, even after the first trip. Yeah, that's a fantastic question.
Ross, what kind of wildlife did you see in your adventures down there?
Oh, yes, oh man, I've been very, very fortunate in a lot of the things that I've been able to do, this being one of them. My first trip down, we saw a heap of Adelie penguins. We saw a bunch of emperor penguins. I mean, obviously from a distance. We actually had one come reasonably close. Like, you're not allowed to go to them. If they come to you, that's fine. And like we just sat down, and we had one Adelie just walk straight up to us and like, what's going on, guys? What's going on? What's up? That same trip saw a heap of seals, but I also saw an orca, which was amazing. That was really, really cool. It was kind of sad because there was an Adelie walking. It was right at the edge of the ice shelf. There was a little Adelie penguin just like walking along, and then there's this orca like chilling right there. It's like, oh, some real nature's about to happen right there. But I mean, it's what it is, that animal has to eat. But I've seen snow petrels, skua are amazing. They're like a seagull on steroids. They're just these really big. I actually like them. A lot of people don't, but they seem like they're actually quite smart, and they're just these really big birds. They also pick on other birds if people don't like them. I've been fortunate enough to go to a couple of there are a couple of Adelie rookeries around. I mean, not go into them, but like go nearby. And see some of the huts around there, because there are some old kind of historic huts around and stuff that you can go and tour. And then this really, really big Adelie rookery. Like you could smell that thing from probably a K1.5 away. It was just foul, no pun intended. But you could smell it before you could see it. It was good. It was good stuff. But yeah, a heap of different animals. And then so for the trip to Tucker Glacier, we were actually with a few biologists, because it's so hard to get up there. We kind of pooled a bunch of teams together, and we ended up collecting soil samples for them that had like nematodes and springtails. There's a bunch of different types of moss and lichen there in northern Victoria. Some of it's like this bright, amazing red. Some of it's like this really interesting yellow. There's some green stuff. There's some pitch black stuff. There's a lot of really, really cool stuff. A lot of really cool wildlife.
So,
When you traveled down there, was it primarily a flight, or were you on a ship?
Yeah, so with the New Zealand program, they do a lot of their science or they shuttle their scientists using either a C-130 Hercules or a C-17 Globemaster. So I had one trip down on a Globemaster, and like that's a 4-hour trip. It's cake. You get on a plane, it's just like getting on a plane, in civilian life. That actually had a helicopter. It was taking a helicopter down. So it's jammed with this helicopter in there. The blades are all folded up and stuff. Then there's like 6 or 7 pallets of stuff behind that. And then there's scientists on both sides of it. So just cram as much stuff and as many people as you can in there and go. The mode of transportation that I've taken the most is actually a C-130 Hercules. And those, this is going to sound stupid, but it's just, they're like a flying tin can. I mean, they're amazing. They're amazing machines, but like they're loud. They're loud and they're full. Like, I mean, with anything, you want it as full as you can get it. So it's chock full of stuff, your own baggage, obviously, but scientific equipment, food, all kinds of stuff is, just packed in on pallets all the way up, like through the center of the airplane, and then you just have scientists on either side just sitting there. But yeah, and it gets, the C-130 actually got pretty cold. Yeah, we had this stuff called ECW, extreme cold weather gear. And so you'd kind of wrap your ECW up into the webbing, and then you kind of pull it around and you just sit there like, better. But yeah. I know the Australian program, I don't know if I'll be able to go with them at all, but they do mostly shipborne stuff. So they're in the process of building an aerodrome at one of the bases that'll, enhance kind of people flying there. But right now it's mostly shipborne. So you take a boat down. My supervisor, Andrew McIntosh, actually was on a ship that got stuck in sea ice for like 6 weeks, about a decade and a half ago or something like that. And so it's just stuck in the sea ice. Like nobody could go anywhere, nobody could do anything, just stuck in the sea ice. So yeah, talk about lockdown on steroids, that one. But yeah.
A basic glaciers question for you, Ross. So we mostly think of probably the alpine glaciers where you have all the ice at high elevation and it's just flowing downhill. But you've got glaciers that are crossing mountains. Does this mean that the east sheet is somehow higher elevation, or did it used to go the other way and it eroded through, or how's that working?
Yes, so the East Antarctic ice sheet is actually, Antarctica in general is the tallest continent on the planet because of the ice sheet. Okay, so the ice is significantly higher. I don't actually think I have any images of the ice divide. No, I don't have any images of the ice divide. I can arm wave at it real quick though. So you have areas where you have basically no ice flowing. Here we go. Let's use that. And I'll just share my screen real quick. So we have East Antarctica right here. We have West Antarctica over here. The ice sheet itself is incredibly thick, on average 2 miles thick. That's the average. So if any of you have ever been to Colorado, if you're standing at the Front Range in Colorado Springs and you look up at Pikes Peak, the 14,000-foot mountain right there, you're looking at ice, or you can think of that as in Antarctica, you would have ice that would be over Pikes Peak from sea level. Okay, so you're looking at really thick ice sheet. In some places it's 4 kilometers thick. Okay, I mean, it's very thick ice sheet. Now, what's likely happened? Let's see. I'm trying to think. I don't think I have any terribly good images. Yeah, that'll do, I guess. So with these outlet glaciers, what you have are likely some kind of structural discontinuity. So there's been a fault or something like that that's actually weakened the rocks, and the ice has actually utilized that as a conduit to move through the mountain system. That's likely, especially in northern Victoria, when this area is just shot through with faults, and you're likely seeing at David and Mawson Glacier as well, where you just have these really large faults that the ice sheet at some point in the past has really kind of taken advantage of. And I mean, the other thing I guess to keep in mind is that Antarctica has been glaciated for about the last 30 months. Okay, the ice actually started growing in a couple of different pockets. The biggest mountain range underneath of the ice sheet is actually the Gimbertsev Mountains in East Antarctica, about right there, and that's probably where the ice sheet actually started to grow from. So, and I mean, several smaller kind of ice caps in this area as well, and those kind of coalesce. But you're looking at millions of years, repeated intense glaciations and kind of retreat. And just this cycle that really starts to produce the landscape that we see. Does that help answer your question, Jeremy?
Yep.
Okay. The other thing that I didn't really talk about just on landscape evolution, that was a different part of my PhD, was actually looking at erosion rates in Antarctica and kind of the landscape evolution for this portion of the Victoria Land coast. And we can use Cosmo to do that work as well, because there's a production zone. There's about a 2-meter production zone for hadrons and about a 30-meter production zone for muons. But depending on how quickly the rock surface moves through that production zone, you can actually work out how quickly the ground surface is actually eroding. So there was a whole component of that. And I didn't mention this, but to actually do the work at Tucker, it was a rock type that was pretty bad, actually. It was what's called a gray wacky. It's like this, the quartz in it is very fine, and it's mostly mud and garbage and crap. It's not a good rock to work with, and that's what I had to utilize to do the work that I was trying to do. So I ended up building a chemical purification procedure to do the work to get the bad numbers from Tucker. So that was a whole kick in the head in and of itself. But those are kind of the 3 broad prongs of my PhD. Any other questions?
All right, I'm going to take that silence as a no. Ross, thanks so much for the talk. This is really fast.
Yeah, not a problem. I mean, it's been fun. It's been a fun PhD, weirdly. It's been really interesting. I mean, that's why it took me 5 years to find a PhD.
Well, it's a heck of a journey, both academically and physically, right?
Yeah. Yep.
Awesome. Well, thanks for joining us, and we'll get a copy of this audio or this video recording to you somehow.
Cool. Good deal. Thanks. Thanks, everybody. Have a great day, or a great evening, I guess, because it's like 6:30 your time, 6:50 your time.
Yep.
Well, have a good evening.
Yep. Take it easy, everyone.